Hello friends, welcome to my channel. My name is Ryan Schul. I hope you've visited this link before. If you have, welcome back. If you have not, then welcome for the first time. So this is all about data science, predictive analytics, deep learning, machine learning, things like that, right? Okay, so today I have a new topic. It's pretty interesting, I think. This is about predicting legal outcomes. We're going to use Python, of course. We use Python for everything. Every example I ever put up here is based on a Jupyter notebook, right? With maybe one or two exceptions, but pretty much Python does everything, right? That's why I use this, right? So it's scalable, up and out, back and forth, in and out, and it does everything, right? So today I want to talk about predicting legal outcomes, and this is important for a variety of reasons. We can try to understand how lawyers can assess cases and the likelihood of winning the case and adjusting strategies according to the probability of winning the case or not winning the case. And I'm going to show you how to do that in just a moment here. And some decisions, this is about how individuals or companies can decide whether or not to settle and go to trial or not, right? Like you have a couple options there. And resource allocation, legal teams can allocate resources and aid and allocate resources to cases with higher stakes and lower probabilities of success. You don't want that, right? You want to boost your probability of success, right? Not depreciate it, right? So risk management, also financial institutions and insurance companies can evaluate legal risks. So why would you go to court? Why would you fight something? What is the outcome? What's the probability of the outcome? I'm going to show you how to do that in just a moment, okay? So that's the point of this case study today. So we are going to go ahead and build a simple classifier, and the classifier is going to predict, is your legal case going to be successful or is it not going to be successful, right? It's a binary outcome. If you think about it, all classifiers are binary and they all produce an outcome. It's success or failure. That's all that is, okay? So it's pretty easy to understand the concept here. It's pretty easy to set up. Let me show you the data set that we're dealing with really quick. This is what it looks like. So we have different features, or just columns. People call them columns in the data science business or in the machine learning sector. It's basically like a column right here. So we have things like internal case ID, gender, race, ethnicity, age at crime. Okay, we have a bunch of these columns. This is going to help us understand the probability of winning the case or losing the case. In this example, we have 133 columns. If I put my mouse down here, you can see 130, right? That's where the count comes from. And if you want to see where the data source comes from, I'm going to give that to you. I grabbed the most recent 2024. Now is the end of March 3/29, 2025. So I got the most recent example I could, right? So usually recency is better. Could be like you have older data that's better, but usually that's the exception, not the rule, right? So I'm trying to get the most recent ones. So I downloaded that into my desktop and put that right here. I'm reading in all of the data into a data frame, and I'm creating a couple of new variables, right? So this is actually called feature engineering, where you create new variables or new features from existing features. So I'm going to go ahead and make sure that these dates are actual dates, because you see this all the time. Dates come in as dates. Sometimes it's a string, sometimes it's a number, sometimes it's a float. That's kind of crazy. Sometimes it doesn't even have any characteristic at all. It could be any different thing, right? But you have to convert a date to a date if it's a real date. A float should be a float. I've seen this in the past where numbers are stored, where dollars and cents are stored as integers, right? So they chop off the decimal places, right? So if you have a 99-cent store and you go in and say, okay, this thing is 99 cents, they'll actually round it up to $1, and $1 is $1 and 99 cents is 99 cents. But if you try to do some kind of reconciliation at the end of the day or at the end of the month, you have to do a month-end tie out. It's not going to be $1 is $1, 99 cents is 99 cents, right? It's not going to be the same thing. They're different, right? So you have to set the data type as the appropriate data type. So that's what we're doing here, okay? So dates are dates, and we're going to go ahead and fill in missing values. And then I'm going to clean up this data a little bit and say if a verdict is a plea bargain, then we're going to assign a 1, okay? So the plaintiff wins. That's the logic here. And if the verdict is acquittal or dismiss, okay, the plaintiff loses. So there's a little bit of cleanup that we have to do on the data because we don't have the actual values in the data, right? So sometimes you have to manipulate things a little bit, but you can use common sense, business logic, just good judgment and decide, sorry, is a verdict a win or is a verdict a loss, right? Like if you don't have that in your data, you have to clean it up a little bit and manipulate the data and convert that into a type that's actually usable. So that's what we're doing here. So let me import the data and run this cell in my Jupyter notebook, okay? And we will import the data, do a little bit of cleaning. And I'm just gonna look at the first 20,000 records right here, because the record set originally was much larger, right? Let me go over here for a second and look at this. 174,000. Okay, so we have 174,000. I tested the model before I started the recording machine here, and actually takes quite a long time to run this. I don't want to suck up hours of time to train and test the model and predict the outcome. I'm going to use 20,000 records. And the data is pretty normally distributed, so it's representative of the entire population. If you take a subset of the population, it should represent the entire population pretty accurately. Okay, and we don't have to train the model on 174,000. If you want to do that, all you have to do is comment out this line, right? Just put a comment over here, okay, and you will get the entire population. It's going to take a while to run, so you have to be ready for that. But if that's what you want, that's fine. But if you take a subset of this population, the outcome is going to be very, very, very similar to the actual population, okay? So I think we can speed things up a little bit, make it run faster, be more efficient, and get essentially the same results without testing every single individual result, okay? So what I'm going to do here is set up my machine learning model with training and testing features and set the independent variable as the X, right? These are going to be all the features that I'm looking for right here. This is gender, race, ethnicity, so on and so forth, up until representation type. And I want to see if this has some kind of impact on whether or not the plaintiff wins. So whether or not the plaintiff wins, is that dependent on gender? Is that dependent on race? Is that dependent on ethnicity? Okay, we live in a culture that is very biased, right? And that's a whole nother video. That's a whole nother topic. I'm not going to get into that. But a lot of these features have an impact on the ultimate outcome. Does the plaintiff win or does the plaintiff lose? So that's what we're measuring here, okay? And they'll tell you why in just a few moments, why we're doing all this, okay? So we're going to label and code all of these features because gender is male or female, right? Race can be black, white, Hispanic, can be a bunch of different things. Ethnicity can be all kinds of different things. If this is not a number, the machine really can't understand what is black, what is white, what is male, what is female. The computer and the whole machine learning concept just doesn't understand text. It doesn't understand labels or text very well, right? So we have to convert these to numbers. So once you convert it to a number, the machine knows 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It knows that very well. It doesn't know male, female. It doesn't know black, white, Hispanic. It doesn't know what that is. So we're going to label that as a numeric representation of what that feature would be, okay? So a male could be 1, a female could be 2. Doesn't really matter. A female could be 1, a male could be 2. It doesn't matter. But you have to understand the context. And once you train the machine, once you convert the data into a representation that the machine can learn and introduce a context, then the machine can go ahead and make predictions of the certain outcome that we're trying to achieve here. So that's what we're doing. So I converted all of the independent variables. This is independent because this can be anything. Independent is like, I'm going to do this, I'm going to do that, I'm going to do all these other things. I'm independent. But what are we trying to predict? Some kind of dependent outcome here, right? That is whether or not the plaintiff wins. So I set up the model, trained it, tested it, got 66% accuracy, right? So higher is better. You want to get closer to high 80s into the 90s, 98, 99% is great. This is only 66%. So this tells me 66% of the time, 2/3 of the time, the machine is going to make the correct outcome of whether or not a plaintiff wins based on these input features right here, right? These are the independent variables. Will the plaintiff win the case or not win the case? So 2/3 of the time, we can make that determination, we can make that judgment, right? But still 33% of the time, we don't know. It's kind of random. And the reason for that is there's a lot of nuances, there's a lot of details, a lot of language. Some lawyers are better than other lawyers. Some judges are biased, some are not so biased. Sometimes judges will say, I'm going to convict the plaintiff no matter what, right? And then some judges are going to say, you know what, I'm going to let this guy go, okay? It doesn't really matter. I'm going to let the guy go. So it's very, very biased. It's very independent, and it's a little bit random. So the machine can only learn a certain amount, right? And make a certain prediction accuracy only up to 66%. And I tested several models. I'll show you that in just a moment here. You can only have a certain percent of confidence about 2/3 of the time. That's it. The other 2/3 is kind of random, and it could be based on somebody's mood that day. Are they hungry? Are they not hungry? I mean, is the judge hungry or not hungry? Are they in a good mood or not a good mood? Like, some of these things are a little bit random. I tested all kinds of models. I'll show you in just a moment how that works out. Okay, so here we have the top 20 features. We have the case type. So the case type a lot of times will determine what the outcome is. The ethnicity of the person being charged with the crime, the court name, race, representation type, age of crime, things like this. So this is called the feature important exercise. This is how important the feature is in determining the outcome of guilty or innocent verdict, right? So the case type, ethnicity, court name, represent, this is like 20%, this is 17, so that's 37%, and 15, 37 and 15, I don't know what the math is, 42% or something like that, probably 42, and then you add another 13. So the top 4 features account for about 50% of the variability of the outcome of, is the person going to be innocent or is the person going to be guilty? Okay, so these top 4 features, and we have 5, 6, 7, 8 plaintiff wins, and there's only 1, 2, 3, 4, 5. There's only 8 because these are the input variables over here. There's only 8 here. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so sometimes there's a whole bunch of features. Sometimes there's hundreds of features. I'm just looking at these 8 right here and trying to assess the outcome of these features to determine the probability of, is the plaintiff guilty or is a plaintiff innocent. Oh, sorry, my cat is stepping on the keyboard here. Okay, so that's what we're looking at here, innocence or guilty, and these features place a lot of importance or a lot of impact into the determination of the outcome, guilty or innocent, right? So let's extract the top 20 features right here, or the top 10. Okay, I got 8 before, so here's the top 10. Sorry, my cat is interrupting. Okay, so again, I ran the algorithm here, and you can see the accuracy is about 70%. And the last example, I think it was just under, like 66%. Okay, so now we're getting up to 70% when we change the features just a little bit. So now 70% of the time, we're able to predict the outcome, innocent or guilty, okay, based on the features that we feed into the model. Now, this is very interesting. I put this into another Python library called Lazy Predict or Lazy Learner. Oh, Lazy Predict, yeah. So I found this thing a little while ago. I have another video just specifically about this. So you can actually train the model on a whole bunch of different, you can train the data set on a whole bunch of different models and see what the outcome is. So this is near centroid. This is 50% accurate, 58 decision tree classifier, 64, extra tree classifier, 66. So this is pretty cool, actually, because you can train this on about 30, give or take maybe 30 something different types of classifying models and predict the outcome for each of these. So the one that I picked, actually, I think this is a little bit old. I just found this library recently, but I think this thing came out a little while ago because I tried this XGBoost classifier, and it's not even in a list as far as I can see. XGBoost, I don't see that here. But the point of this is to loop over lots and lots and lots of different models and compare each one with its ability to make a prediction on the outcome. Again, this is guilty or this is innocent for the plaintiff, right? So all these models are running and we get the probabilities of each one's outcome, and we can see none of them are great. But I think it's okay. I think it's okay because there's so many nuances that go into this. The model just can't learn all the dialect, all the back and forth discussion between the judge and the prosecutioners and the plaintiff and the defendant, right? There's so many variables. You can't possibly capture all these variables. There's too many nuances. It's too complex. So if you have a model that is 70% accurate, in this case, we got 70% accuracy, and you can determine the outcome of that case 70% of the time accurate, maybe 30% of the time you'll make a mistake, I think it's still a value add, because I'll tell you what, I'm not a lawyer, but if I was, I wouldn't want to go to trial for a case if I think, okay, I'm probably going to lose the case. And if you think, well, I have no idea what the outcome is going to be, why would you even go to trial, right? Like, this kind of tool helps you understand, am I going to be successful in the trial or am I not going to be successful? Again, it's a binary outcome. There's only two decisions that can possibly happen. But if you think 70% of the time you can be accurate and you can be successful, then go for it. By all means, do that. And you can help the person, you can help the plaintiff, you can help the jury, and you can help society too, right? If you know basically what the outcome is. If it's just random and you don't really understand what's happening, that's kind of nonsense. You're wasting your time, you're wasting everybody's time, right? So if you can get 70% accuracy, even though it's not great, it's not perfect, because there's so many minute decision variables that go into this actual final outcome, the final decision, it's impossible to say, right? You'll never get better than probably 70%. Maybe you can dial it up to 71%. That's it. And you can see all these classifiers I ran, they got 50%, 58, 64 most of the time, and we got 70%. So I think that's still good. So let me run this cell right here. And this is where the rubber meets the road, guys. So let's say you have all these variables, right? And this is what comes to you as a lawyer. You have the case type, you have the court name, ethnicity, and case indictment, and the race, the person's color, right? The race and the ethnicity. So if you have all these variables, this is what you would put into the model after you trained it, after you tested it, after you did everything. You refine the model, clean up the data a little bit, made your final decision. This is your case right here. This is literally your case, right? Based on the model's training, testing. Sorry. Sorry, I have a little bit of a cold. So based on the model's training, testing, and ability to predict the outcome, this is your specific case that you're dealing with. This is what you would put in, and this is the decision that you get. So we will go ahead and run this cell, and we see all the possible outcomes here: Hispanic, non-Hispanic, docket, felony complaint, IDV. I don't even know what these things are. Some of these IDV, individual, criminal. Not sure what these are, what some of these things are. But again, like, we're looking at the whole case that the lawyer is bringing to the court and training the model and trying to understand what the potential outcome is, okay? So for a new case coming to the court, we can put in this information. All you'd have to do, train the model, test the model, put in this information. What is the gender? And these are the variables here, right? Okay, so it should be pretty obvious. Age, court, representation type. This is what the input would be, okay? So this could be anything. Gender, I mean, it can be male or female. That's it. The race can be whatever you define here. Ethnicity is non-Hispanic or Hispanic. Age or crime. These are all the variables that impact the decision of the judge at the end, right? And if you put in these variables based on this predicted outcome, you would lose the case, right? 67% of the time, just over 2/3 of the time, about 66 to 67% of the time, you would lose the case. So as a lawyer or as a legal representative of the legal system, again, I'm not a lawyer, I don't know how these things really work, but I would tell you from a data scientist perspective, you would not take this case based on these inputs right here. 1, 2, 3, 4, 5, 6, 7, 8. And again, you can customize this, and you can train this a bunch of different ways. This is just one representation of the truth, okay? So you can tweak the model, you can change it, you can add to it, you can subtract from it. But I'm saying based on these inputs and based on historical outcomes, you would lose this case 67% of the time. So as a lawyer, you would not take the case, right? You're going to lose it. Your plaintiff is not going to win the case, so don't take it. So I'm just trying to say, if you're a lawyer, you can use machine learning to try to improve the outcome and change the probability of your work, right? That's what we're trying to do today. And again, like this is dependent on the judge's names, the court name, the case type, the locations. There's a lot of variability over here. That's why we only get up to, where is this, 70%? Yeah, the best case I could get was 70% accuracy. I couldn't get better than that. I could not do that. I tried. I tested all these models. I tested 30-something models. And the actual model I picked wasn't even in this list. I think this library is a little bit older. So if you take this model, it actually gets a better precision, better accuracy of the outcome. All these models are only getting like just over 60%, somewhere right at 50%, right? There's so many nuances, there's so many details, there's so much language, back and forth discussion, and a lot of opinion and a lot of bias too. You can't predict bias. You can't predict randomness, right? So that's it. That's my take on predicting legal outcomes. I have some notes over here. You guys can read it. I'm not going to like spoon feed all this information, but basically the takeaway is the model is trained, tested, tried to generalize and make assumptions or make predictions into the future, what the outcome is going to be. We focus on adding different variables. Again, you can customize this. You can add a couple more variables. You can subtract some variables and see if that helps you improve your outcome. These are very flexible. These are very scalable. These are very changeable. You can change these models to be anything you want, okay? And at the end, like all I'd say, there is an ethics consideration and there's limitations to what the model can do. There's bias, there's explainability, there's legal restrictions, right? And we're all human, so there's a human component too. Can you predict humanity? No, you really can't. You can't do that, right? So I'm trying to predict mathematically and statistically what the outcome is going to be for a lawyer going to trial based on training and testing of the model and these inputs right here, right? So the new case data, black male, not Hispanic, 29 docket, King, criminal court, Ackerman, Andrea, that is the judge's name, and historically, how has a judge decided, right? What kind of decisions is this judge coming out with? And representation type, retained attorney. Based on that, we know that this case is going to lose, and we have a 67% chance of the case losing. That is a probability. Now, you could win the thing, right? You have a like 33% chance of winning the thing, but it's not likely. So as a lawyer, I wouldn't take this. I wouldn't take the case. I wouldn't take the case, right? But if the inputs are different and you have a higher probability of winning and a different court system, different judge, different race, different age, sorry, kitty, then maybe your probability would be higher. That's why you have to change these inputs over here. You'd have to change the inputs, and when you change the inputs, then the output is different too. Okay, so hopefully that was insightful and educational and inspirational for all you future lawyer types. Again, I'm not a lawyer. I don't know how these things work. I know data science, I know mathematics, I know statistics, I know finance, and I hope that works. But I'm trying to take the principles and apply that to predicting legal outcomes. Okay, so hopefully this was a good use of your time. I'm going to wrap it up. I will post all this code. I will share all the code with the video, and I'll see you guys in the next one. Thank you for your time. Take care. Bye.